Let's try this again. All right. So, stoichiometry. That's where we are for the next couple weeks. Stoichiometry is the study of relationships. It's the study of relationships between different chemicals. Now, I told you way back in September that September the conversions are going to look like this. And then in October, they were going to look like this. Yeah, and today, from here on out, for the next few weeks, they're going to look like this. Now, if you mastered this and mastered this, then this is really easy. If you slacked off on these, then you're going to need a little more work. Okay? And we're going to be practicing. I'm going to get you back warmed up to back where we were. You can do this. Don't panic. Unless you want to panic, in which case, whatever. Okay, so remember when we use these T-charts, we use conversions. And our conversions is thing on the top and a thing on the bottom. Like 1 dozen is 12. If you look at your speedometer doing 65 miles per hour, that means you're going to go 65 miles in 1 hour. Okay? They're not fractions. Okay? These are not fractions. You can't divide one by the other, and you should never divide one by the other. They are conversions, meaning the top and the bottom are the same thing with different units. 32 grams of oxygen is equivalent to 1 mole of O2. 1 mole of O2 is equivalent to 32 grams of oxygen. If you look at the mole ratio for the combustion of water, or the creation of water, it takes 2 moles of H2O, or you make 2 moles of H2O for every 1 mole of O2. Okay? So, stoichiometry is relationships between moles of one thing and grams of the same thing, which you've already done. You've already done. Grams of something and its volume, which you're going to learn about pretty soon. Moles of one thing to molecules of the same thing. This you've already done. How many molecules are in 1 mole? Yeah, 6 times 10 to the 23rd. So if you remember, there is 6 times 10 to the 23rd molecules of O2 in 1 mole of O2. You learned this way back when. We're going to use that too. Now, where things get interesting, and why this is its own unit in January, is we start changing chemicals. We can think of moles of one thing to moles of another thing. From moles of A to moles of B. Like moles of O2 to moles of H2O. For every 1 mole of O2 you burn with excess hydrogen, you will make 2 moles of H2O. For every 2 moles of H2O you separate through high voltage, called electrolysis, you're going to make 1 mole of O2. Now, we can also do this. This isn't terribly useful, but we do it every now and then. Moles of one thing to mass of another thing. And then the most useful stoichiometry we do is mass of one thing to mass of another thing. I have to do this when I do demonstrations for you. Okay. Remember when we did the zinc and the sulfur outside? I had to do the calculation to determine how many grams of zinc I needed for how many grams of sulfur I had. You're going to do this too. When you're doing your reactions next week or next week, you're going to have to calculate how many grams of sucrose do I need for this many grams of this chemical. Make it go fa-whoosh and not go. Because if you don't calculate it, it goes, and we'll all laugh at you. Like, you did it wrong! If you do it right, it goes, gaboosh, makes a giant pile of smoke, and people in middle school are like, must be stoichiometry. Giant pile of giant smoke cloud rising over the school.
Oh, sweet. You know what? Can't wait for
And the last thing we're going to do is something called percent yield, where we learn about how much we should actually expect to make. Percent yield is how many cookies you make when you have so much batter. It would be great if you had 2 kilograms of batter and you got 2 kilograms of cookies, but chemistry doesn't work that way. And neither does cooking. That's percent yield. Okay, now there's a couple things we need to remind ourselves of, and they're huge, so pay attention. when we're doing a T-chart, whether it be 1 step or 6, what we start with goes right here. What goes in this box here? Nothing. And in every box, there are how many things? You don't remember? 3, exactly. In every box, there are 3 things. Please write this down. 3 things. Things in each box. 3 things. What are they? They are the number. They are the unit. And they are the label. 3 things in every box. Number, unit, label. But Mr. Byers, do you really need all that? Yes. Because if you come to me and you say something like, I don't get it, I'm going to look at your work. And if I don't see all 3 things, I can't point out where you've made mistakes. Mr. Byers, I don't get it. How come 1 doesn't divide by 2 and give me the answer I want? Because I have no idea what 1 means. I have no idea what 2 means. You need the unit and the label so these things can tell you what you're dealing with. Also, they will cancel out. Because whatever you have here, you'll move down here. For instance, if you have 1 box of gunk, then you're going to convert down box of gunk down here. So eventually, box of gunk will cancel out. Okay. The numbers don't convert, but the unit and the labels do. Every box needs to have 3 things. A number, a unit, and a label. What does every box have to have, Michael?
A number, a unit, and a label.
Thank you.
Looking or
Gavin, why can't you be more like Michael? Okay, so this is just a quick review. We've done these a million times. You might have actually even seen this slide. Our starting unit, our starting number, our starting unit, our chemical, those are our given. Somewhere over here you want to write down your goal. And then in every step, you bring down your unit and your label, and then you write whatever you're converting to. Once again, 3 things. Today we're going to practice what we've done back in October, 1-step T-charts. We're going to practice that. Tomorrow we'll practice 2-step T-charts. Practice that a bunch. Then by the end of the week, we'll actually do mass-to-mass stoichiometry, the really effective, useful part of stoichiometry. Yep. Okay. Now, every time you write something up here, you have 2 options. 2 options. Option 1. This matches your goal, and you're done. You can do some math now. Do a little bit of math. Option 2. This does not match your goal. You bring your unit down and convert again. Okay. Option 1. Your unit and your labels match your goal, so you're done and you can do math. Option 2, it doesn't, you need to bring it down and do another conversion. And you just keep doing that system. Do I have what I want? Nope, do another conversion. Boom, do I have what I want? Yep, I'm done, now I can do math. All the numerator divided by all the denominator. Just like any function in math. Everything on top, divided by everything down below. Okay. Any questions so far? Give me a thumbs up if you remember last year. If you remember what you were doing in September and October of 2018. No. Some of you need to get off the wacky tobacco and the... Yeah. Stop introducing yourself to Mary Jane. I don't remember what I was doing. Okay.
Are you talking about the devil's lettuce?
Yes. Or the devil's dandruff. You're doing okay. Davin's like, it's medicinal. All right, so It helps me deal with life. Important points to remember. Don't do any math. Don't do any math until you have your goal. Don't do math in your T-chart. No math should be done in your T-chart. Don't do any math until you have your goal. Once you have your goal, then you do math, but not before. But it says 2 moles and I multiplied by gram per mole. Shouldn't I multiply the periodic table by 2? No. Don't do that. No math until the very end. Next, don't carry down numbers. Only units and labels. So you're like, got it? We did that last year. Check your math. Watch for division errors. Remember, guys, your calculator is stupid, but it's very hardworking. Okay? You cannot ask your calculator to think for you. You can ask for it to work for you, but you can't ask it to think for you. You have to do the thinking. It can only plug the numbers in that you added to it, or you punched in. Calculators are very hard workers, but they're very bad thinkers. Cars, same thing. You can't get in your car and say, take me to Joe's house.
Actually, if you have a Tesla, you can.
Actually, Charlie can do that.
Daddy boy.
Actually, if you go to Tesla with the autopilot. Okay,
Do they
so
even have gas
No,
pedals?
he didn't buy 2. He didn't buy 1, he bought 2.
you bought 2? Okay.
Wait, what is it called? Is it a gas pedal or is it like an energy pedal?
It's an accelerator.
Oh. There you go.
Moving on. So I'm glad you guys got the analogy and you're ready to move on. Okay. So is your number reasonable? If the exercise is asking you for grams of copper and the answer you got is 46,000, there's a very good chance it's not a reasonable calculation. Because what we try to do is give you exercises you might encounter. How many grams of copper do you need to react with 34 grams of sodium? 89 billion. There isn't 89 billion grams of copper on the planet. So, no, okay?
Oh. It's only 89.
On the other hand, if you get 0.1 grams, 0.2, that's probably reasonable. Get the idea? All right. Now, listen very carefully. Very, very carefully. If you need to inhale and exhale to settle down, that's a good thing to do right now. Okay. Are you ready?
Yeah.
You can never convert from grams of one thing to grams of another thing. It doesn't exist. It is impossible. You cannot convert between grams of oxygen and grams of hydrogen. There is no single conversion that gets you from grams of one thing to grams of another thing. There is no conversion that gets you from grams of sodium to grams of chlorine. The only way you can change chemicals is a mole ratio. The mole ratio is the only time you should ever see 2 different chemicals on top and on bottom of the same block. For instance, you might see mole of sodium to mole of chlorine. The only time you should ever see 2 different chemicals in the same area, the same top and bottom, is if it was a mole ratio. You should never see gram of one thing to gram of another thing. You should never see gram of A to mole of B. You should only ever see mole of A to mole of B. This is the only time you should ever see 2 chemicals, is when it's a mole ratio. Give me a thumbs up if that makes sense. Okay. Put your hand up and wave it around if you don't understand. All right, cool. So, how do you change chemicals? If you can't convert right to one or the other, you have to get your grams of A into moles of A. Use your mole ratio to go from moles of A to moles of B. Then use your periodic table once again to go from moles of B to grams of B. Everything that we're going to do in stoichiometry, except gas density, you have already done in pieces. All you're doing now is putting the pieces together. Like when you play with Legos and it says, make this little part of the car, make this little part of the car, make this little part of the car, and then put the three things together. That's what we're doing now. Everything we've done, everything we're doing except gas density, you've already done in pieces. Now, you're just going to put them together. Okay, so, any questions before we move on? All right, let's warm our brains up and remind ourselves how molar mass works. Once again, molar mass is an average of all the isotopes. It's how much a mole of something weighs. If you somehow could, and you can't, but if you somehow could weigh out a single mole of oxygen, it would weigh that amount. That molar mass is read grams per mole. Now, when you do grams per mole, it always looks like this. It's a number of grams, I'll just go ahead and use oxygen, over 1 mole of oxygen. Do not put grams per mole in their own box. It's gram in one box, mole in another box. Or gram in one box, mole in another box. Because how many things are in each box? 3. Not 4, 3. Okay, so what I'd like you to do now is I would like you with the periodic table, you might need a calculator too, what I'd like you to do is determine the molar mass of these 5 things. Determine the molar mass of these 5 things.